Our next topic is stress due to temperature changes or thermal stresses. Let us consider one homogeneous and uniform bar. Homogeneous and uniform. That cross section of the bar is uniform. Homogeneous and uniform bar of length L. It is kept freely on the horizontal surface. Kept freely. Freely on the horizontal surface. Now let us consider the temperature of the bar has been increased by an amount delta T uniformly. So delta T is temperature rise is temperature rise uniformly. That is, all point temperature rise is same amount by delta T. Uniformly rise the temperature by an amount delta T. Then what will be the length of the bar? The initial length was L. Now due to temperature rises, it will increased by L alpha delta T. So now the length becomes L plus L alpha delta T. This is the increase in length L alpha delta T. Where what is alpha? Alpha is coefficient of thermal expansion. Coefficient of thermal expansion. So now as the length has been increased, what is the thermal strain? Thermal strain. This is thermal strain. Thermal strain. That is increase in length L alpha delta T by initial length, that is alpha delta T. Now what is thermal stress? Thermal stress is 0 because the elongation is not restrained. That is, it is naturally, it has been increased its length, so there is no restraint of the elongation, so thermal stress will be 0. So it has 0 thermal stress and thermal strain is alpha delta T. Now let us consider one situation. The same bar of length L is kept between two fixed supports. A and B. And at initial condition, the rod or bar has 0 stress and strain. 0 stress and strain. From that, the temperature of the bar has been increased by delta T. Uniformly. That is, at all point, temperature rise is delta T. So now, uniform temperature rise is delta T of the same bar L. Now, the bar cannot elongate as this is kept between two fixed supports. That is, as cannot elongate, that is thermal strain is 0. But this rod, when it cannot elongate, because of what? These two fixed supports are producing a compressive force P and P. Due to that, it cannot elongate. Now what is the value of P? That is, or what is the thermal stress? Thermal stress sigma is what? P by A. But value of P we cannot find out from equation of statics. That is, this is a statically indeterminate problem. indeterminate. Statically indeterminate. So now we have to apply one boundary condition to find out the value of P. So what we will do, that is, we shall consider that support A is present and support B is redundant. Support B is redundant. Support B is if support B is redundant, then what happened? This bar will elongate. This bar will elongate. This bar will elongate by an amount L alpha delta T. This elongation is L alpha delta T. Now what is the activity of the support B? It is providing a compressive force P. So B is providing a compressive force P. So due to that, these two, the combination of these two, that is, if there was no support, it will elongate to this. As there is a support, it is providing a compressive force. Due to this combination of these two, the resultant elongation of the bar is 0. That is, the resultant elongation of the bar is 0 because it is fixed between two fixed support. So what is thermal elongation? L alpha delta T. L alpha delta T is thermal elongation. Now compression by support B will be what? Plus compression of support B, P, length is L, E, and cross sectional area is A. That is equal to 0. So what is the equation? Equation we get L alpha delta T plus PL EA is 0. That is, P by A is E alpha delta T. Obviously, there will be a minus sign. So, P by A is what? That is nothing but the thermal stress. So, thermal stress is minus E alpha delta T. Negative sign implies that the stress is negative. As stress is compressive. Negative sign implies that the stress is compressive. So the amount of thermal stress we have determined, that is minus E alpha delta T. So this is the amount of thermal stress will generate when this bar is kept between two fixed supports and uniform temperature rise is delta T. Now let us solve this problem. A steel tube 2.5 centimeter external diameter and 1.8 centimeter internal diameter encloses a copper rod of 1.6 centimeter diameter to which it is rigidly joined at each end. This figure shows this schematic, that is, this is the steel tube, and this is the copper rod, and this is the steel. This is steel tube. Steel tube external diameter is 2.5 centimeter, internal diameter is 1.8 centimeter, and copper rod has 1.6 centimeter diameter, and they are rigidly connected at each end. This is the connection, they are rigidly connected at each end. If at a temperature of 20 degrees Celsius there is no longitudinal stress, this is the longitudinal direction, and it is given at 20 degrees Celsius, longitudinal stress is 0. Calculate the stress in the rod and the tube when the temperature is raised to 210 degrees Celsius. Now initial temperature was 20 degrees Celsius. Now temperature is raised to 210 degrees Celsius. So what is the temperature difference or temperature rise? That is 210 minus 20 is 190 degree Celsius. So temperature rise delta T is 190 degree Celsius. And additionally, it is given that ES means Young modulus of steel is 210 GPa. Alpha S is coefficient of thermal elongation, that is 12 into 10 to the power minus 6 per degree Celsius. EC is Young modulus of copper, that is given 100 GPa, and alpha C is 20 into 10 to the power minus 6. Now we can note that alpha C is greater than alpha S. Alpha C is 20 into 10 to the power minus 6 and alpha S is 12 into 10 to the power minus 6. Now at 20 degree they have equal length, say L. Now if they are not rigidly connected, if we let them elongate freely to 210 degrees Celsius, then what happens? That is, say this is one connection and other connection is redundant. That is, at this end is free and we are left them to elongate naturally at 210 degrees Celsius. Then what happens? That the copper tube will elongate, say somewhere here. This is the copper tube. This is the length of copper tube at 210 degrees Celsius. If we left them to elongate freely. Now what will be the length of the steel? As steel has less coefficient of thermal elongation, steel will elongate little bit less than copper. This is the steel tube. This is the steel tube, which has elongate bit less than the copper. This is the steel tube. So this is steel and that is the copper. Now the question is that they are rigidly connected at both ends. So at any situation their length will be same. As they are connected, they are not free. They are connected by two rigid support or rigidly connected there. So their length at any situation will be same. So at 210 degrees Celsius, what will be the length of them? Their length will be somewhere here, that is in between steel and copper. So what happens? That is, copper will be compressed by some amount, this amount, copper will be compressed by this amount, and steel will be elongated by this amount, this amount. Steel will be elongated by this amount. So copper tube will be compressed and copper rod, this is copper rod will be compressed and steel tube will be elongated. So force on steel tube will be in tension and copper rod will be in compression. Now let us draw the free body diagram at 210 degrees Celsius. That is, at 210 degrees Celsius, if I draw the free body diagram, say this is the copper and this is the steel tube. This is copper, this is copper, and this is steel. This is steel. Now what are the forces? Copper will be compressed and steel will be elongated. Now say the stress on copper that has to be determined. What we have to determine? We have to determine, calculate the stress in the rod and tube when temperature is raised to 210 degrees Celsius. Now say stress on copper is sigma C and stress on steel is sigma S. Now at equilibrium, all summation of force along longitudinal direction is 0, that is, this is x direction. So what we can write from this, sigma SAS minus sigma C AC is 0. What is AS? AS is cross sectional area of the steel tube, and AC is cross sectional area of the copper rod. Now what is cross sectional area of steel? That is pi by 4, 2.5 square minus 1.8 square. We are taking area in centimeter square because both side. So that will be, we can equal to sigma C pi by 4 1.6 square. So from this we'll get, if we calculate it, that is sigma S is 0.85 sigma C. So this is the equation of statics. This is the equation of statics, and there is no force along y direction. So that is summation of F(y) is 0. That equation becomes redundant here. So we have one equation and two unknowns. What are two unknowns? Two unknowns are nothing but sigma S and sigma C. So two unknowns, and we have only one equation. So that is a statically indeterminate problem. So this problem is a statically indeterminate. Sorry, statically indeterminate problem. So what we have to do now? We have to apply one boundary condition. What is that boundary condition? We have discussed earlier, that is, at any situation as they are connected rigidly at both ends, their length will be same. So what will be their length at 210 degrees Celsius if they are connected by rigid supports? The rigid supports are providing a compressive force to the copper rod, and tensile force to the steel tube. So their length at 220 degrees Celsius will be same. Now let me establish the boundary condition. The initial length of both copper rod and steel tube was L. Now at elevated temperature delta T, if we allow the copper rod expand freely, the length of the copper rod will be L plus L alpha C delta T. But when there are these rigid walls, the rigid wall will provide a compressive stress sigma C to the copper rod. So due to sigma C, the compression of the copper rod will be, so if it is compressed, that's why this will be minus sigma C L by EC. So this is the final length at elevated temperature of the copper rod. So here, if I show you here, so this is the final length. This is the final length of the copper rod. Now, what will be the final length of the steel tube? What will be the final length of the steel tube? Initial length of steel tube was L. At elevated temperature, if we allow the steel tube to expand freely, then it will expand to L alpha S delta T. And whereas here it is not expand freely because of these rigid walls. So the rigid wall will provide a tensile load to the steel tube. So due to that tensile stress, the elongation will be elongated, so it will be further plus, so sigma s l e s. So this is the boundary condition, because at elevated temperature both the copper rod and steel tube have same length, so their length are same. Now we can cancel L in both side and we can rearrange the equation like alpha C delta T plus, sorry, it will be minus sigma C EC is alpha S delta T plus sigma S E S. So this is my boundary condition. Now put the values, you will get a relationship between sigma C and sigma S. That is, our equation is alpha C delta T minus sigma C by EC is alpha S delta T plus this. Now let us put the value of all parameters. What is alpha C? Alpha C is 20 into 10 to the power minus 6 into 20. Sorry, delta T is 190. Sorry, 190 minus sigma C. Sigma C we have to determine sigma C. What is EC? What is EC? EC is 100 and ES is 210 and alpha S is 12. So now let us put the value. EC is 100 GPa, that is into 10 to the power 9, that will be equal to alpha S. What is alpha S? 12 into 10 to the power minus 6 into 190 plus, what is that we have to determine also, and ES is 210 into 10 to the power 9. 10 to the power 9. Now we got another relationship between sigma C and sigma S. What is that relation? We got already that sigma S is 0.85 sigma C. We got this relationship already. Now let us replace the sigma S, that is 2 into 19 into 10 to the power minus 4 minus sigma C 100 into 10 to the power 9 is 12 into 19 into 10 to the power minus 5 plus, that is sigma S is 0.85 sigma C to 10 into 10 to the power 9. So from this equation, we can determine sigma c. Now determine sigma c, you will get sigma c is 108.2 MPa. If this is determined by putting the value of sigma c in this equation, that is, say this is equation 1 and this equation is equation 2. Now putting the value of sigma c into equation 1, you will get the value of sigma s. Sigma s is 91.97 MPa. So we have determined the stresses both in copper rod and steel tube. A steel cube with all faces free to deform. All faces are free. Young modulus is E, Poisson ratio is mu, and coefficient of thermal expansion is alpha. The pressure hydrostatic stress, the pressure or hydrostatic stress developed within the cube when it is subjected to uniform increase in temperature delta T. So the steel cube is kept freely. It is free to expand in all directions and temperature is uniformly increased by delta T. So what will be the stress developed? Hydrostatic stress or pressure developed within the cube. As it is free to expand, the stress developed within the cube is 0 because no strain is restrained here. So elongation is not restrained, so stress will be 0. For free expansion, stress is 0. For free expansion, stress is 0. So option A is correct. This is the correct answer. And this is from GATE 2014. A 200 mm long stress-free rod at room temperature is held between two immovable rigid walls. Let me draw the configuration. This is the 200 mm long stress-free rod held between two immovable rigid walls. Say, let me give a name, that is walls are A and B and length is 200 mm. So initially stress is 0 at room temperature. The temperature of the rod is uniformly raised by 250 degrees Celsius. That is delta T is 250 degrees Celsius. Uniformly raised, that means all point on the rod having same temperature rise by 250 degrees Celsius. If Young's modulus and coefficient of thermal expansion, that is E, are 200 GPa, E is 200 GPa, and value of alpha is given, that is 1 into 10 to the power minus 5 per degree Celsius respectively. The magnitude of longitudinal stress developed in the rod has to be determined, and this has been asked in GATE 2014. Now, if we allow the rod to expand freely, then it will expand by which amount? That is it will expand by delta L amount, that is L alpha delta T. But these two immovable rigid walls do not allow the rod to expand. Then what happens? they will produce a compressive force. These two supports will provide a compressive force to the stress free rod, and due to that compressive force, stress will be generated, and that is the thermal stress, and that stress we have to calculate. That is the longitudinal stress, because stress is along longitudinal direction, along this direction. This is the longitudinal direction. So we know that this is a statically indeterminate problem, because what the compressive force P we cannot determine. So what we have to do? We have to apply one boundary condition, and first of all we will consider that support B is redundant, that is there is no support. If support B is redundant, then at elevated temperature, that is delta T, when 250 degrees Celsius, this rod will elongate. How much will be the elongation? That is, this is delta L, that is L alpha delta T. Now, what is doing by support B? Support B is providing a compressive force. Support B is providing a compressive force, say that force is P. And the boundary condition is that due to thermal elongation, and both combination of thermal elongation and force P, the net elongation is 0. Because net elongation is 0, because these two immovable support do not allow the bar or do not allow the rod to elongate. So the boundary condition is that is resultant elongation delta is 0. With these two effect, the resultant, with these two combination of these two, the resultant elongation is 0. So what is elongation due to temperature rise? That is L alpha delta T. What is deformation due to force P? That is PL by EA. Now what is stress developed? Stress developed in the rod, that is nothing but P by A. Stress sigma is P by A, because P force is subjected to the rod by the rigid supports or rigid walls. So P by A is nothing but the stress. So we can write L alpha, this equation becomes 0, because this is the resultant elongation. So this is equal to 0. So L alpha delta T plus P by A is nothing but sigma. So sigma L by E is 0. So from this we can write sigma is minus E alpha delta T. So we got the expression sigma is minus E alpha delta T. This negative sign implies negative sign implies that stress is compressive. So here compressive stress will generate, and what will be the value of that stress? We have to just put the values. E is 200, alpha is 1 into 10 to the power minus 5, and delta T is 250. So 200 into 10 to the power 9 into 1 into 10 to the power minus 5 to the power minus 5, and delta T is 250. Now 2 into 250 is 500 minus 500. 2 into 250 is 500. Sorry. This 2 into 250 is 500. Now that becomes, there are two zeros and 9, 10 to the power plus 11 minus 5 is 10 to the power plus 6. This much PA, and that becomes minus 500 MPa. So longitudinal stress becomes 500 MPa and nature is compressive. So this is the answer to the problem. Now let us move to the next problem. A circular metallic rod of length 250 mm. This is the length of the rod is shown 250 mm. Is placed between two rigid immovable walls as shown in the figure. These are two immovable walls. Let us give a name A and B. The rod is perfect contact with the wall on the left side, that is at A, and there is a gap of 0.2 mm. This gap is shown. There is a gap is 0.2 mm between the rod and the wall on the right side, that is at B. If the temperature of the rod is increased by 200 degrees Celsius, that is delta T is 200 degrees Celsius, the axial stress developed in the rod, and that unit should be in MPa. So we have to calculate the axial stress, that is stress along this direction. This is the axial direction. What will be the stress at elevated temperature? And it is given that Young modulus of the material is given. E is 200 GPa and coefficient of thermal expansion is 10 to the power minus 5 per degree Celsius. So alpha is 10 to the power minus 5 per degree Celsius. Now similarly here the same problem, same like previous one. If we allow the rod to expand freely, the elongation of the rod will be delta L is L alpha delta T. L alpha delta T. Let us calculate the value. L is, what is the value here? L is 250 mm. 250 into 10 to the power minus 5 into delta T is 200. Calculating this, we will get 0.5 mm. So the rod will elongate more than the space available or gap available here. So what happens? After elongation of 0.2 mm, the walls, rigid walls A and B will not allow the rod to elongate by providing compressive force P, and that compressive force will generate stress inside the rod, and P by A is the value of stress. So what will be the stress? We have to apply boundary condition, that is here, the net elongation delta is nothing but 0.2 mm. 0.2 mm. So what is elongation due to thermal expansion? That is L alpha delta T, and deformation due to force P is PL by EA, that is equal to 0.2 mm. So here we have to take care of unit first, or we can, as they are in SI unit, we can convert it into SI unit. So 0.2 mm we can, that is 0.2 into 10 to the power minus 3 meter. We'll consider, or we'll convert all units in meter, otherwise there may be a error due to units. So L is what? Here value of L is 250 mm. L is, so L in SI unit this much meter. So L 0.25. We have already calculated the value of L alpha delta T this much mm, that is 0.5 into 10 to the power minus 3. So let me put the value here directly. Actually we have calculated it earlier. So 0.5 into 10 to the power minus 3 plus P by A is sigma. So sigma L by E is 0.2 into 10 to the power minus 3. Let me calculate it. What is the value of sigma?
sigma L by E is minus 0.3 into 10 to the power minus 3. So what is the value of sigma? Sigma into L is 0.25, E is 200 into 10 to the power 9 is minus 0.3 into 10 to the power minus 3. From this, sigma becomes minus 0.3 into 200 into 10 to the power 9 minus 3, that becomes 10 to the power 6 divided by 0.25. That is minus 60 divided by 0.25 into 10 to the power 6 sigma. So sigma becomes minus 240 into 10 to the power 6. This was PA, Pascal in SI unit. So 10 to the power 6 means MPa. That is minus sign here, another minus sign, that implies the stress is negative here also, and the value of stress is 240 MPa. Here 240 MPa. So stress developed in the rod is 240 MPa. So this is the answer to the problem, and this was asked in GATE 2016. Now let us move to the next problem. A solid steel cube constraint on all 6 faces. That is, first let me draw the steel cube. All 6 faces are constraint. So this is the cube. This is the steel cube. And all 6 faces are constraint. That is, they cannot move or elongate. So the steel cube cannot elongate, as all 6 faces are constraint. Now is heated so that temperature rises uniformly. Uniformly means all point temperature rises delta T. If thermal coefficient of the material is alpha and Young modulus is E and Poisson ratio is mu, the thermal stress developed in the cube due to heating is to be determined. Now let us consider that this is X, this is Z, and this is Y direction, and length of each side of the cube is L. So X direction, length is L. Now if we allow the cube to elongate freely, then along X direction elongation will be delta L, which is L alpha delta T. Now but here the steel cube is constrained in all 6 faces, so it cannot elongate. So what will happen? That is, all 6 constraints will provide compressive force in each direction, and that compressive force will cause stress in the cube. That is, say along X direction 6 stress is sigma X, along Y direction compressive stress is sigma Y, and along Z direction stress is sigma Z. As this is a uniform, and this is a cube is uniform, so here sigma X will be equal to sigma Y will be equal to sigma Z. And this condition, when sigma X, sigma Y and sigma Z are same, it is called hydrostatic stress. Hydrostatic stress. And we can consider that sigma X is equal to sigma Y equal to sigma Z, and that is equal to sigma. Now we have to calculate what is sigma, that is the thermal stress developed inside the cube. But this is a statically indeterminate problem, we know that. So how to calculate it? That is, in any direction, let us consider, we are considering X direction, the length or in x direction, the resultant elongation of the cube will be 0. That is, resultant elongation is 0. If resultant elongation is 0, we can consider that resultant strain along x direction is also 0. If resultant elongation along x is 0, then resultant strain along x direction is also 0. So the boundary condition is that resultant strain is 0. What is thermal resultant strain? That is thermal strain along x is epsilon Tx plus hydrostatic strain due to this hydrostatic stress. So combination of these two or resultant of these two is 0. Now what is thermal strain along x direction? Thermal elongation is L alpha delta T. So thermal strain will be L alpha delta T. Thermal strain will be L alpha delta T divided by L. That is elongation divided by initial length. Now what will be hydrostatic strain? We know that epsilon Hx or epsilon x is what? 1 by E, or better, let me write down in generalized term first. Generalized Hooke's law that can be calculated from generalized Hooke's law. Epsilon x sigma x minus mu sigma y plus sigma z. So here epsilon x is nothing but 1 by E. Sigma x, sigma y, sigma z is 0. All are sigma. So we can take common sigma. 1 minus 2 mu. Sigma x equal to sigma y equal to sigma z, and that is equal to sigma here. So, or we can write hydrostatic strain along x direction is 1 minus 2 mu. So plus sigma by E 1 minus 2 mu is 0. So here alpha delta T plus sigma by E 1 minus 2 mu is 0. That is, sigma becomes minus E alpha delta T divided by 1 minus 2 mu. Minus sign implies that stress is compressive. Now let us check which option is correct. Here we can see that option A, alpha delta Te divided by 1 minus 2 mu. So this option is correct one. So this is the correct answer. And this has been asked in GATE 2012.